Today we are going to see about the Unit 3 of Embedded and Real-Time Systems. The Unity consists of program design and analysis. Here we are going to see about models of program assembly, linking and loading, compilation techniques, and the program level performance analysis and software performance optimization techniques, and the program level energy and power analysis and optimization, then analysis and optimization of program size, and the program validation and testing. First of all, we are going to see about components for embedded programs. First one is state machine. The reaction of most systems can be characterized in terms of input received and the current state of the system. The finite state machine style of describing the reactive system behavior. Finite state machines are usually first encountered in the context of hardware design. So this is the software state machine program. So this is for automatic seat belt warning system state diagram. Here there is an ideal state, seated state, and belted state, and buzzer state. If the passenger not wearing the seat belt, means it automatically switch on the buzzer, or otherwise it automatically give the permission to move the car. So this is the pseudocode for seat belt timer. So here we can see if seat is in case ideal condition. If seat is belt seated, means the timer on is true. Otherwise, the seat belt is belted, means it won't hear the buzzer. Else, if the buzzer will be on. So coming to case belted state, this is switch case state. If seat state is ideal, if else if the belt state is seated. Coming to buzzer state, if seat belt is belted, the belt is turned off. Then switch else if the seat state is ideal, then seat turn off the buzzer. So there are 4 switch cases statements. So each statement we can check this condition. Then if the passenger is not wearing the seat belt, means the buzzer should be on. Then next one is stream oriented programming and circular buffers. This is another one of the program tools which is used to do the embedded programming. The circular buffer is a data structure that handles streaming data in an efficient way. The size of window does not change. The fixed size buffer to hold the current data. To avoid constantly copying data within the buffer, move the head of the buffer in time. The buffer points to the location which the next sample will be placed. Every time add sample automatically overwrite the oldest sample, which is one of needs to thrown out. When the pointer gets to end of this buffer, it wraps around the top. So this is the diagrammatic explanation of the circular buffer. The next one is queues. The queues are also used in signal processing and event processing. Queues are used to whenever data may arrive and depart at somewhat unpredictable times, or when variable amounts of data may arrive. A queue is often referred to as an elastic buffer. The next coming for models of program. Programs are collection of instructions to execute a specific task. The models for programs are more general than source code. The source code can't be used directly because of different types of such as assembly language and C code. The single model to describe all of them. This is called control and data flow graph. It's a fundamental model for program. So we can use the control for data flow graph for the explain the program flow of the both languages, that means assembly language and as well as high level languages. So coming to data flow graph is a model of program with no conditionals. In a high level programming language, a code segment with no conditions have only one entry and one exit point. This one is a basic block. So here this is a placing path. So W is equal to A plus B and X equal to A minus B, Y is equal to X plus D is a sum of the examples for basic blocks in C. So an extended data flow graph for our sample basic block. So here you can see the diagrammatic expression for W is equal to A plus B. So here we can obtain the W by using A and B values by adding these two values. So round nodes denotes the operators and square nodes denotes the values. The standard data flow graph for our sample basic block is shown in figure. Then control data flow graph. Control data flow graph uses data flow graph as an element, adding construction to describe control. The CDFG having following 2 types of nodes, that is decision node and known as data flow nodes. The decision is used to describe the control of sequential program. Then data flow nodes enclose the complete data flow graph to represent data. So this is C code for data flow graph. So rectangular nodes represent the basic blocks. The diamond shaped node represents the conditionals, and label nodes conditions. Then edges are labeled with the possible outcomes of evaluating the conditions. So here left side you can see the C code, and right side you can see the corresponding control data flow graph. So CDFG for a while loop you can see like this. So while loop left hand side you can see the while loop condition, and right hand side you can see the control data flow graph for the particular while loop. So next we are going to see about the assembly, linking and loading. So this is the main process of coding the embedded product. So assembly and linking, the last steps in compilation process. They convert list of instructions into image of the program's bits in memory. Then loading it puts the program in memory so that it can be executed. The compilers used to create an instruction level program into assembly language code. The assemblers are used to translate symbolic assembly language statements into bit level representation of instruction known as object code, and also translating labels into addresses. The linker is used to determining the address of instruction. The loader loads the program into memory for execution. Then absolute address. The assembler assumes that the starting address of ALP has been specified to the programmer. The relative address means specifying the address start of the file address to be computed later. So coming for assemblers, the assembler translates the assembly code into object code. Also assembler must translate opcodes and format bits in each instruction and translate labels into addresses. The labels, it is an abstract provided by the assembler. The labels knows the location of the instruction and data. So label processing requires two passes. That is, first pass sends its code to determine the address of each level. In the second pass, assemble the instruction using label values computed in the first phase. So this is the code and the simple table for example. So this code used to store the load and store the data by subtracting the data R0 and R0, R1. So right side you can see the corresponding symbol table for label 1, label 2 and label 3. So next is linking. Linking allows the program to stitch together several smaller pieces. The linker operates on the object file and links between the files. Some labels will be both defined and used in the same file. Other labels will be defined in a single file but used elsewhere. The place in the file where label is defined as known as entry point. The place in the file where the label is used as the external reference. The phases of linkers are two phases, that is first phase and second phase. In first phase, it determines the address of the start of each object file. In second phase, the loader merges all simple tables from the object files in a single large table. So next we are going to see about the program level performance analysis. So the technique we use to analyze the program execution time are also helpful in analyzing the properties such as power consumption. The CPU executes the entire program at the rate of we desire. The execution time of a program often varies with the input data values. The cache memory has a major effect of program performance. The cache behavior depends in part of the data values input to the program. The execution time of an instruction in a pipeline depends only on that instruction, but not on the instruction around it in the pipeline. So this is the symbolic representation, diagrammatic representation for the execution time. So by using this total execution time, you can calculate this by using this cache memory and pipelining architectures. Next one is program performance measuring techniques. So for program performance measuring techniques, we have some components called simulator, timer and logic analyzer. The simulator runs on a PC, takes input and executable for the microprocessor along with the input data and simulates the program. In case of timer, it can be used to measure performance of execution sections of code. The length of the program that can be measured is limited by the accuracy of the timer. By using logic analyzer, it is used to measure the start and stop times of load segment. The length of the code that can be measured is limited by the size of the logic analyzer. The types of performance parameters, that is average case execution time, the worst case execution time, the third one is best case execution time. Coming to average case execution time, this is typical execution time we would expect for a typical data. In case of worst case execution time, the longest time that the program can spend at any input sequence is clearly important for the system that must meet deadlines. In case of best case execution time, the measures can be important in multi-rate real-time systems. The elements of program performance is calculated by the execution time, that is program path plus instruction timing. The program path is defined as the sequence of instructions executed by the program. By instruction timing, it is determined based on the sequence of instructions traced by the program path. Not all instructions take the same amount of time. The execution time of instruction may depend on the operand values. So measurement driven performance analysis. To measure the program performance, need CPU simulator. Measuring program performance, combination of determination of the execution path and limit timing of each path. So cycle accurate simulator is one of the simulator which is used to find out the program performance. Then coming for software performance optimization, loop optimizations and code motion, then induction, variable elimination and strength reduction. These are all some of the techniques to be used for software performance analysis. For code motion, it can be move unnecessary code but out of the loop. So we can remove the unnecessary codes in the loop. So you can reduce the instruction length. Then reduce the instruction length, you can reduce the program size and you can reduce the program execution time also. So here we can see, before we can see if I is equal to less than n cross m. By using this n star m, we can use called as temporary one. So we are introducing temp1 variable instead of n star m. So the loop bound computation is performed on the every iteration during the loop test. Okay. So by using this temp1, the overall program size will be reduced when compared to before step. Okay. So we can avoid n cross m minus 1 unnecessary execution of the statement by moving it before the loop. So by using this technique, you can reduce the program size. Thank you.